the correlation of data, and the visual representation, which would be a scatter plot. Now this is when we have bivariate data, so we're comparing two sets of data. So scatter plots, here's an example of one. So the data I've used here is some yearly exam results. So they're actual results from, I forget how many years back now, but they're actual results that happened in year 11 exams once upon a time. And I've plotted the mass extension results up against the actual advanced results. But the thing with a scatter plot and correlation, you've got to use the same sets of data. So the mathematics results are only there for the students that did mass extension as well. Because obviously there would be nowhere to plot the ones that don't do mass extension. It's got to be the same sets of data we're using. There is the English extension versus English advanced, so same sort of idea. And that one there is mass extension versus English extension. See if there's a relationship between those sets of results. That one is mass extension versus business studies. And then the last one is mass extension versus PDHPE. If we wanted to compare these different sets of data. Now, what a correlation then is the strength of that scatter. And it should lie in between -1 and 1. Right? They always lie in between -1 and 1. Now that first one there, the mass up against mass extension, has a correlation of 0.81, which we would classify as a strong correlation, and we'd sort of expect that. We'd like to think there would be a strong correlation with the results of extension and results of 2 unit. I mean, it's all mass. Hopefully you would like a strong correlation there. English, the correlation wasn't as strong, still moderate, what we would call moderate, got a correlation of 0.49 that particular year. Is that unexpected? Well, maybe it's a bit different in English because the English extension course and the English 2 unit course aren't really like mass extension and maths, where there's a really tight connection with maths and mass extension, whereas English, they're like two totally different courses really, aren't they? And of course, well, there's no reason why there should be a strong relationship between mass extension and English extension. Still got a positive correlation, but we would call that one a weak correlation, so 0.23. Business studies, again, logically, why would you have a strong relationship between those ones? And this one came out at 0.01, so virtually no correlation between those two sets of data. And the interesting one here is the PDHPE end up with a negative one, also weak, but again, there's no reason why there would be a correlation between these two subjects. What do we see here when it changes from positive to negative? If you had to draw a line of best fit, basically you're talking about the slope of the line. Once you get to that PDHPE one, you can sort of see that if I was going to draw a line of best fit, it probably is going to have a negative slope. So any graph, we put the independent variable on the horizontal axis and the dependent variable on the vertical axis. But when it comes to this bivariate, it's not always obvious which one's the dependent data and which one's independent, because maybe there's not. And so it really doesnn't matter which axis you put the different data on. We're going to be looking at linear correlation. That's what we're interested in. But of course, it doesn't have to be linear. You could have non-linear. You could have something like this where you'd say, oh, actually, there's a really strong exponential correlation. You look at that and it's looking like an exponential curve. You could have a hyperbolic shape. So hyperbolas usually represent inverse proportion. So there's an inverse correlation there. I suppose you could have a quadratic correlation. I have no idea what sort of data that would be, but theoretically it's possible the data could fall out like that. You have a quadratic correlation. As I say, we're going to be interested in linear correlation, and as I was saying, that's where the line of best fit comes in, and we'd like to then get an equation for that line, and that will allow us to make predictions. Now when we're doing our line of best fit, we identify multiple points using larger circles, because you might have two sets of data that's exactly the same, but by putting a circle around it, it reminds you actually that point's there twice. You're doing your line of best fit, you know, oh, actually there's two at that point, so that might change your decision on lines of best fit. Oh, and if it's more than twice, yeah, then you put the number in there. Okay, hey, this one happened 5 times or whatever. Okay, so back to our mass extension one. If I wanted to draw in my line of best fits, usually just by eye you do it. That's where I put my one. You're trying to get as many close to the line as possible, basically. You're trying to get it as tight as you can to that line. So that's where I placed my line of best fit. Now, assuming that all that data is reliable, then you can make predictions. And there's two different types of predictions. You can interpolate the data. So interpolation is when you make predictions within your data set. So in this case, I could say, well, looking at this data, I would kind of predict that someone getting 40% in extension, well, yeah, they probably would get 70% in the advanced. And then there's extrapolation, and that's when you make predictions that are actually outside the data set. So here's something crazy. Not the example I've got here, but here, theoretically, if I was to extrapolate this data, someone who got 0 for mass extension, they probably got 50% for T10. Well, I mean, that's a bit of a crazy one, but that's extrapolating the data. You take it outside the data set that you know. This brings up this idea of the difference between correlation and causation, and it's probably one of the biggest mistakes people make with correlation. Just because there is a correlation does not mean it is true. What you use correlation for is to work out whether this warrants further investigation. So if you saw a good correlation, you think, oh, hang on, maybe there is something here. So you go, okay, maybe I'm going to set up some experiment or something to investigate this further to see actually if there is a link between these two things. Here's an example. During summer, people get hay fever. Also in summer, there's a lot of pollen in the air. So there actually is a strong correlation between the presence of pollen and hay fever. Well, therefore, pollen must cause hay fever. That's the conclusion that we're drawing. But again, that's just a correlation, so you go and do further investigation, and actually there have been studies that do prove that. So that actually is a sensible correlation. Whereas this one, during summer, the sales of ice cream increases. But also during summer, deaths by drowning goes up as well. Okay, well therefore, we've got a strong correlation between ice cream sales and death by drowning, so I'm going to draw the conclusion that ice cream causes drowning. Okay, warrants further investigation, and I'm pretty sure if we investigated that we'd find out, no, that's not what is actually happening here. Rather than people looking at it, which people do with correlation, they just go, oh well, this must be true, look at the correlation. That's not what correlation is about. Correlation is about picking up things that warrant further investigation. So that's not a sensible correlation. They're just both things that happen in summer more often because it's hotter. So more people are swimming, you get more deaths by drowning. It's hotter, so more people are going to eat ice cream. Correlation does not mean causation. All right, there we go. 15D.